Hi, so today we'll be talking about the cortical microcircuitry of the marmoset posterior parietal cortex in the context of a cognitive task. So why do we care about this? We know that schizophrenia patients have impaired executive functioning, and we can see this in tasks that require visual discrimination and target selection. We also know that schizophrenia patients have cortical thinning, especially in the supragranular layers, and that might underlie some of the behavioral deficits that we see. We know that the frontoparietal network underlies these kinds of behaviors, but we don't actually know that much about the local microcircuitry of key nodes of this network, like the posterior parietal cortex. And this is largely because the predominant non-human primate model, the rhesus macaque, has a heavily gyrated cortical surface, which makes accessing some of these key regions like PPC or DLPFC a lot trickier when you want to do these laminar experiments. And that's where the common marmoset comes in. With its smooth cortex, these regions like DLPFC and PPC are actually a lot easier to access. And they also have many other advantages that lend themselves well to neuroscientific research. We also have shown in recent evidence from our lab and other labs that the marmoset's frontoparietal network is largely homologous to that of the macaque and humans as well. So this lends itself really well to the current question, which is investigating the local laminar microcircuitry of the posterior parietal cortex in the common marmoset in the context of a cognitive task. So the NeuroPixels probes are what we're using to do these experiments because the large number of contacts along this narrow shank allow us to record from a large number of units across multiple cortical layers simultaneously. What are the animals doing while we're doing these recordings is a simple target selection task where they're presented with a marmoset face in the absence or in the presence of a distractor stimulus, which is this black dot here. And they have suppress a response to this black dot and make a saccade to the face. And we can see that the distractor does impact their performance, where when there's no distractor, they're more accurate and slightly faster at making their saccades. So this suggests that there's some sort of target selection that's happening, and what we're interested in is the neural correlates of this behavior. So we were able to record from a large number of units, over 3,023 sessions. And of these, a quarter of the units showed significant visual or saccade-related activity during the task. These units were roughly evenly distributed across the different cortical depths, but what I hope you can appreciate is that they're doing different things at these different depths. And this is what we want to disentangle from this project. And while this is an ongoing project, I do have some preliminary data with regards to the timing of these effects that I can talk to you about now. So for the 945 task modulated units, we can determine the onset of the visual response and look at how this varies across the different cortical depths. And so here I have the onset of the visual response on the x-axis and the distance from the cortical surface on the y-axis. And we can see that it's actually at these intermediate layers that we get the earliest visual responses. Another thing that we can do is we can look at the units that actually discriminate between the target and the distractor when it's presented in the contralateral hemifield. And we can see that 167 units can discriminate between the target and distractor, and of these, 80% prefer the target. We can then look at the onset of this discrimination at the different cortical depths, and we can see that these superficial units are actually the ones that are discriminating between target and distractor earliest. And we can see that there's a sort of nice organization of the visual inputs at these intermediate layers and these discriminations at these superficial layers followed by these deeper layers. So the last thing that we can see is that for the 134 units that prefer the target stimulus, 50% of them actually have higher activity on correct trials as compared to incorrect trials. So taking all of this together, we can see that marmoset PPC contains units that discriminate between target and distractor, and of these units, a large chunk have increased activity on correct trials, suggesting that these units play some sort of role in target selection. And this is exactly what we would expect based on investigations of marmoset PPC. What's novel in our work is we've been able to disentangle what's happening at different layers, showing that these intermediate layers get the earliest visual inputs, whereas these superficial layers have the earliest discrimination time between the target and distractor. This suggests that these supragranular layers play some sort of key role in the early process of visual discrimination and target selection, and that the thinning of these cortical layers may lead to less efficient discrimination and might underlie the deficiencies that we see from these patients on these tasks. That's all that I have for today. Thanks for listening to my talk, and let me know if you have any questions.